This is a binary stiffness compliant mechanism that can be changed from a stiff state to a compliant state and back by triggering a bistable switch at its center. When the switch is extended, the mechanism is stiff, but when the switch is triggered inward, the mechanism exhibits near zero stiffness due to principles of stiffness cancellation. To understand how this mechanism works, consider first this simpler mechanism. Note that although its flexures appear deformed, they are not. They are actually fabricated in the curved configuration shown and thus store no strain energy until they are deformed by a load. When their shuttle is forced to the right, the system exhibits high stiffness as its flexures are stretched according to this force displacement plot. When the shuttle is forced to the left, however, the system exhibits a region of near zero stiffness as the positive stiffness of the top two flexures cancels with the negative stiffness of the single bottom flexure as it is compressed. This region of near zero stiffness continues until all three flexures begin to stretch again and the system rapidly stiffens. If you'd like to learn more about stiffness cancellation to better understand why the force displacement plot achieves a region of near zero stiffness, be sure to see part 1 of this mini-series about binary stiffness compliant mechanisms. If the same mechanism had been fabricated so that it begins leaning to the left instead of to the right, its force displacement plot would be the same shape but would be shifted up to the right instead as shown here. Thus, if we fabricated both left and right leaning mechanisms so that they are both attached to the same grounded body as shown here, and then a bar were inserted between them to join their shuttles together so that all their flexures are arranged in parallel, i.e. they all experience the same shuttle displacement, the force displacement plot of the combined mechanism would result from adding the force displacement plots of the two individual shuttles together. Note that the slope of the resulting plot is large everywhere, and thus the mechanism is stiffly constrained over its full range of deformation in both directions. If we then replace the long bar with a shorter bar by pulling and pinning the two mechanism shuttles closer together, their individual force displacement plots would also be shifted inward as shown here, since the short bar essentially resets each mechanism's resting equilibrium position. And, since the short bar also forces all the now preloaded flexures to be arranged in parallel, the combined mechanism's force displacement plot can again be found by adding these two force displacement plots together. Note that the resulting combined force displacement plot achieves a region of near zero stiffness centered about the mechanism's resting equilibrium position. Thus, if a bistable mechanism is then used to replace the long and short bars, the mechanism can be switched to either achieve the stiff or compliant force displacement plots as desired. You can see that as the mechanism is loaded by an Instron machine over a large enough range, the mechanism can be triggered from its stiff to its compliant state, where it remains as it is cycled back and forth. Note that in its stiff state, the mechanism achieves a stiffness of 14.47 newtons per millimeter, and in its compliant state, it achieves a stiffness of negative 0.18 newtons per millimeter. If you're still confused about how this mechanism works, you can read more about it in our published journal article. A link to the paper is provided in the description below. The paper was recently selected as the best paper from among all of the other papers published in the Journal of Mechanisms and Robotics in 2021. Finally, I wish to acknowledge Dr. Reinier Kuppens, who designed, fabricated, and tested this mechanism while working in my lab at UCLA as a visiting scholar from Delft University of Technology. Thanks for watching The Facts of Mechanical Design.